which is because of d over dz equals 0 of u and d over dz square of w is equal to 0. And you end up at this expression. W is proportional to v multiplied by the tangent theta multiplied by z divided by h. Okay? And you plug this thing in the equation from the beginning, okay? In the Fourier equation that we had at the beginning, u, v, w, with this particular solution, and you end up with the frequency omega equals 2 times omega tangent theta h over alpha. So look at here how it is. Here it was 2 beta c alpha squared. Okay? Imagine we neglect the beta here. Alpha divided by alpha squared. This is a 1 over alpha. Okay? That I recover here. The 1 over alpha. Okay? So a simple geometrical effect can make the same effect as the variation of the rotation of the Earth when you see it at a local position depending on the latitude. Okay? And these are certainly you saw that on the web. Okay, you type Rossby waves and you have a lot of these wonderful photos. Okay, so that was the Rossby wave. If so, up to now, to observe these waves, or the waves that Greenspan observed in '76, you see that you need to have a little thing in the flow that vibrates. If you stop vibration, there will be no wave. Okay, you agree with that? Okay, the flow is susceptible to have waves, but you have to give energy to see these waves. And up to now, I had a little objects and to observe these waves. Okay, now we come back to what is called internal gravity waves, the waves that we can observe with stratification. These waves are much more natural to us. It is like a pendulum, okay? You take a pendulum and this oscillates. This is exactly the same with a fluid. You have a fluid which is stratified, so heavy fluid here, light fluid here. If you take a little piece of fluid which is, you take this one that was heavy, I put it here at the top here, of course it wiggles down. But as it possesses a certain inertia, it will go further. And after, as it is denser than the ambient fluid, it will have a positive buoyancy and will come back. Okay, it's like a balloon that you put in a swimming pool. Okay, you put a balloon under the water, it comes back, and it does that. So the fluid is doing that. You can write the same equation as before. Earlier equation here. So no rotation. Okay, no Coriolis term here. Here I have a change in the vertical velocity. I have a vertical pressure gradient and the buoyancy. And the buoyancy can be written under this form here. It is equal to minus m squared W. And that says that the buoyancy force, in fact, is the change in density versus z. Okay? If you have a fluid which is at higher density here, it will have a tendency to push the balloon. Okay? The water will try to push the balloon up. Okay? And you can recast this thing under this shape with a frequency, which is called the Brun-Vasarya frequency, which is minus 1 over rho d rho dz, so a change in rho compared to rho, if you want. This is a logarithmic derivative, multiplied by g. Okay, so this is an inverse of the square of the time, so this is the natural frequency of the system. So this is the reason why I write the equation with W like that. Again, you solve this equation, and you end up with this equation now. Omega squared is equal to n squared, the one here. And now it is not a cosine square as I had before. For the inertial wave, it's a sinus. Okay? So this, you see the two equations are very similar. One has the angle between the axis and the wave vector, and the other has the angle between the wave vector and the horizontal axis. Okay, so these are visualization from a satellite of this gravity wave in the stratosphere. Okay? These waves, I promise, these waves will play a tremendous role in the future. Okay? all our meteo code for weather forecast neglect these waves because their wavelength is about 1 kilometer. And when you want to solve the weather on the size of the planet, you cannot have points so close. So in fact, what they do in meteo, they try to parameterize these waves. So they say, I have a big storm here. I may have emission of waves in the stratosphere. So I said, minus 4% of energy that will go in the stratosphere. Okay, and they do that with their nose for now. Okay, so that's why there are a lot of studies in oceanography the same, in meteo the same, to try to understand these waves when they are sent in the stratosphere, where, at what occasion, what is the energy that they bring with them, and so on. Okay, and this is a visualization by ambroscopy, shadowgraphy. You know, you try to read the contrast of a flow because of the change of density, and that was done in 2007 by a Japanese colleague. The dispersion relations, examples is here, and what else? You see that here also you see that there are dispersive waves. So we continue to play. We have inertial waves and thermal waves. We can try to mix both, yes? So I take a stratified flow and I rotate the flow. And if you solve the equation, this is the same as before, except that you have a Coriolis force here, okay? And you have here also the divergence less of the flow, and you Fourier transform everything, and you end up with this expression, omega square as a function of the wave number, capital omega square, n square, and this can be written under this form. 4 omega square cosine square plus n square sine square theta. Okay. In fact, this dispersion relation was studied for the first time, and in detail, I would say in 2005, by colleagues of us. Okay, people we meet in conferences. Okay, only in 2005. You see, this is quite recent. These waves are known for maybe 1 century or approximately. Okay, from Poincaré or a little bit before, and but to study them in the lab, people took a lot of time. Okay? In fact, the first mention in the Journal of Fluid Mechanics, which is our Bible, okay, is in '76, where they did some experiment with rotation and stratification. So this is the first appearance of this in the modern era of science, I would say, after the war. So this is quite recent. You see that these waves are also conical shape. And the dispersion relation can be plotted under different shape. Okay? When you rotate, something very particular, when you rotate and when you are stratified, the waves cannot exist anywhere with their frequency. Their frequency is always between, this is because the sine of the cosine shape, always between n and 2 omega, and 2 omega in geophysics is called f, the Coriolis parameter. So this is, all the waves are between omega and f, or between f and omega, depending on the stratification versus the rotation. Okay? So they exist only there. This domain, you have no waves can exist in the flow. Okay? So if you perturb the flow, you will have no oscillation by a viscous damping, because you have viscosity. Okay, so the perturbation will be damped and will disappear. Okay, something which is more difficult to make a calculation. It takes 2 pages of handwriting, but I can explain the way to calculate these things. Is when omega, the rotation, is the function of the space. And this happens, for instance, when you have a hurricane. Okay, the velocity, the rotation in the center of the hurricane is big or small at the beginning. After you have solid body rotation, so this is constant omega, and after you have a decrease. Okay, usually it's a Gaussian shape. Okay, so the rotation itself is a function of space. So you see, when I will make the Fourier transform with exponential I alpha x plus beta y and so on, I will have big problem with my omega. Okay, with the terms coming from the Coriolis force. So the way to solve that, and this is a general features in a non-homogeneous media where you have waves, is to say that the wave number of a wave is itself a function of k. Okay, so you search for a solution with a wave, but the k, the wave number, is itself a function of time. And when you do that, it's a trick that physicists know. And when you do that, you end up with, to simplify the system of equations that we have, which is quite complicated. Because here you have all the terms, okay? You have u grad u and u grad u, u here being the omega as a function of space, the rotation. And you end up with this equation to solve. d alpha over dt plus omega beta equals 0, d beta over dt minus omega alpha equals 0, and gamma d gamma over dt equals 0. This means that the wave you are looking at, so imagine this is my wave number, so the wave is like that, okay, propagating like that, and now this thing rotates, okay, at the same omega as the fluid itself. Okay? So imagine you have a source here, you have a wave, but this wave rotates. Another one here, the wave will rotate also, okay? So this solution is much more complicated. But we end up with this expression for the dispersion relation, 2 omega, omega the rotation, omega z is the local vorticity, and when you calculate it, is equal to 2 omega plus r d omega dr. Okay, this is a term that you have to calculate when you come from that. So 2 omega omega z, and you see that this term is, you just replace the 4 omega square that we had before. Yes? Remember we have 4 omega square, gamma square, and so on. Now we have 2 omega omega z. And if you d omega over dr equals 0, you recover the 4 omega square. Yes? So this equation is quite simple when you know that omega z is the vorticity. But now you can ask, you can have a question: is it possible that omega omega z, that this term is negative? So what's the meaning of that? The square of the frequency will be negative. So the frequency itself, we have an imaginary part. Okay? So that means that you have a growth rate. So that means you have an instability. Okay? So certain, if you want to solve a problem of a fluid that rotates with a certain shape, you solve the stability problem, which is in fact the dispersion relation of waves that you solve in it. Okay? And this is possible if this omega z is negative, and this is the condition here, d over r square omega over dr is less than 0. And in fact, this is called the Rayleigh criterion, and it is this is simply the centrifugal instability. And to observe this instability, and these are examples here, maybe you heard about the Taylor instability. You have 2 cylinders, you rotate you have fluid between, you rotate the inner cylinder, and you make vortices which are torus like that, one of the other. Okay? And Taylor, in 50-something, discovered this instability and gave his name to this instability. Okay? So this is G.I. Taylor, the big G.I. Taylor. So this is the centrifugal instability that we see arriving, in fact,